Okay, students, Assalamu alaikum. Welcome to today's lecture. Okay, today, before we will not cover a new topic, we have just completed the topic of synchronous generators and synchronous motors. So I've released the assignment regarding that, and let me share my screen with you. And I've also released the complex engineering problem. Okay, so we are just going to discuss the two assignments, especially the complex engineering problem, and we will not do anything new today. Inshallah, next week we will start the DC machines. Okay, so I hope you can now see this is the my view of the LMS. And if you go in the current week, which is November 9th to 15th November, today we are at 13th November. So I have posted both the lectures which were conducted on Monday and Wednesday. And I have also posted assignment 3, and I posted it on yesterday, 12th November, and the due date is 1 week after 12th November, which is 19th November. Click on this, you can see the assignment 3. I hope you can all see this. So it has two problems. One is related to a Y connected synchronous generator, and one is related to a delta connected synchronous motor. Okay. So you have to solve these two problems in assignment 3, and you can also look at assignment 4, which is released today, 13th November. So the due date is 2 weeks. Since it is a little bit involved problem, you have to think about it. And the due date is 27th November, which is 14 days from now. So you have to submit both the assignment 3 and both the assignment 4. Both are from CLO3. Let's look at the assignment 4. Today, in today's lecture, I'm just going to discuss this. Nothing new. We will start DC machines from next week. Okay. And okay, so it says it is 13 November released today, and 27 November after 2 weeks it is due, and the due time is 9 a.m. On the LMS, the time is also mentioned. So if you look at the LMS for assignment 3, also the due time is 9 a.m. and for complex engineering problem is also 9 a.m. Please refrain from sending it on WhatsApp and my email. Even the previous cases are pending because I'm so busy. I hardly get enough time to look at this stuff that I have to go through all my emails to try to look for somebody's assignment which he was lazy not to submit on time on the LMS. So please submit on time. Please submit on LMS. Otherwise, you are going to be in a lot of problems. You are going to be in a lot of problems because I cannot go through. You can imagine I am a head of department and I get around 50 to 60 uh, applications from students. And since it is online mode nowadays, all the applications are coming on emails and they are coming on my WhatsApp, and it is becoming very hard. And sometimes your email goes into the spam folder, and I'm just looking in my inbox, so it creates a lot of problem. So, like good children, just submit it on time. Even if it is unfinished, submit it on time. Submit it on LMS and within the due time. So I can find all the assignments at one place in one go, and I can mark them. Okay, so we are now discussing the complex engineering problem and what you have to do in it. Okay, so I've given you this 2 weeks time for this. Okay, in this complex engineering problem, it is related to a synchronous motor. And just let me scribble something on the whiteboard. The whiteboard. Share whiteboard. Okay, and I'm taking my lectures nowadays in English because of Abdullahi, who is an international student. So Muhammad Saim assignment one issue. Yes, I got it. I got an email through Yasir, but as I told you, I'm too busy. It's very difficult for me to go through the emails and WhatsApp. So if you didn't submit on time, you will have to face this issue. And because you are irritating me, I will also irritate you. Whenever I will have time, then I'm going to check it. Okay, because I have so many pending issues. We have to submit the PEC application before 30th November, and we have to look after the admission campaigns, and we'll also have to look after many other things, the research papers and the research work and the PhD thesis students who are nearing their completion time. So there are lot many issues. Don't think just that I take a class and I go home and enjoy. So I have got many administrative and many academic issues to deal with. So that is why I always plead with you that always submit it on time and submit it on LMS. Okay, so what I was trying to tell you about this complex engineering problem. So basically what you are going to do is, I hope you can all see this whiteboard. Everyone can see this whiteboard? Let me check. New share whiteboard. Okay. New share whiteboard. Okay. So what I have told you about the synchronous motors is that synchronous motors has this unique ability that you can either run them at a leading power factor, or you could run them at a lagging power factor. Okay, you could run them on a leading power factor or on a lagging power factor, and in order to make it go into the leading power factor, you could do one of the two things. You could make it over excited, which is that you can increase the field, and in order to go in the lagging power factor, you could make it under excited, which is the decrease of the field. And in order to go into the leading power factor, you could reduce the mechanical load. And in order to go to a lagging power factor, you could increase the mechanical load. Okay, so these are the two mechanisms. You can change work, play with the field of the synchronous motor, or you could play with the mechanical load of the synchronous motor, and then you can make it go into the leading power factor and into the lagging power factor. Okay, so we have already discussed this detail in the last class. The recording has already been made available on the LMS, and in these two methods, I've also told you how does it impact the phasor diagram, and how, for example, if you change the excitation of the machine, that means that EA becomes constant, because EA is a function of K into phi into omega, and phi is the main field which is on the rotor, and omega is the rotational speed of the rotor, and both of these things parameters are constant. So if you are not changing the field of the machine, then what happens is EA vector is just swinging in an arc. EA vector is swinging in an arc like this. Let's say this is V phi up till here. Okay, so this EA vector is swinging in an arc, and when EA comes here, the machine goes into a lagging power factor, and when EA goes here, the machine goes into a leading power factor. So this is when you are working with the field. And similarly, if you are changing the mechanical load of the machine, that what happens is that the torque angle increases. Sorry, if you are not varying the field, okay, I take my words back, let's repeat. If you are not varying the field of the induction motor, then stays constant. Okay, the magnitude of EA stays constant if you are not varying the field of the machine, and it is just swinging in an arc. And when EA comes here, it is working in a leading power factor, and when EA comes here, it is working in a leading power factor, and over here as a lagging power factor. And if you change the mechanical load of the machine, this thing happens. And if you change the excitation of the machine, then obviously EA is proportional to the field on the rotor, and the magnitude of EA definitely increases. So if this is V5, initially EA was this, it was in a lagging power factor, and if you increase the excitation of the machine and EA becomes bigger in magnitude like this, and then the machine will obviously go into a leading power factor. Okay, so these are the two mechanisms. I have completed this in detail yesterday, and you already know about this. You can look at the previous lecture. Now what we are trying to do is that we are going to harness this property of the synchronous motor, and we are trying to make it uh, uh, being used as a power correction device. So those of you who have studied ENA with me, there was some problem that I had given you in the ENA course, in some maybe test or an assignment, I don't know, in which I had told you that you want to do a power correction. So you know most of the loads in our home in are inductive loads. And because of the inductive loads, the power triangle looks like this. This is your real power, this is your reactive power, this is the apparent power, and the this angle theta being the power factor, and the cos of this angle is being the power factor. So you have two situations. One situation is this, and one situation in this in which theta is very less. This is your reactive power, and this is your apparent power. Obviously, you can see that theta 1 is much greater than theta 2, and what it implies is in this triangle you are always paying the K electric bill for the apparent power, and you are consuming the real power. Okay, so when the theta 1 becomes very high, for example this case, if the theta 1 becomes very high, so you end up paying for vector A, which is apparent power, it is this, and the real power is much less than this. So you end up paying much more money than you are actually consuming. So this suboptimal behavior is due to the fact that most of the loads in your home are inductive. So you also have a portion of the reactive power, and this reactive power is just like a imaginary power or like a false power that is not being used, because all the components like this capacitors and inductors, they have a unique property that they can store energy in the form of electric field for the capacitor and the magnetic field for the inductor. So they are not actually consuming this energy, they are just converting it from one form of the other. When they are storing it, they store it in the form of electrical field or a magnetic field, and then they just return to the circuit, because in a AC circuit they are constantly charging and discharging, because the direction of the current becomes reversed every now and then. So this reactive power is actually not being consumed by you, it is returned back to the K electric. But since the mechanism of K electric is that they want to charge you for the apparent power, so in this case, you are paying much higher for A than what you are using real power, which is P. And in this case, you can see that A is much higher than P because of this triangle. And in this case, A is approximately equal to P. So you are not paying much more than what you are using. So all industries, especially in the residential homes that you live in, you already have inductive loads like fans and the water motors. And your power factor, if you look at the display on the electric meter outside your home, if you have the new ones, the digital meters, then you can see that when you just switch on the lighting loads in your home, the power factor will be very close to 1, like 0.95, 0.96. And when you switch off all the fans and the water motor, then you can even see it decrease to 0.8. And if your power factor is very bad, then it can even go to a value like zero point 0.6 or something. Because I tried this experiment in my home, and the power factor in the worst case it decreased to 0.64 or something. So 0.64 is a very bad power factor. It almost means this situation. Okay, it almost means this sort of a situation. Okay, please turn off your video because I'm just getting image which is moving. Okay, please turn off your video. Anzala and Asadullah, you are frequently turning on your videos and I get some distraction on my screen. Asadullah and Anzala Sumro, please switch off the video. We are working with the audio. Okay, because your this thing pops up and I can see some moving videos and which is disturbing to me. Okay. Okay, please everyone turn off their videos, please. Okay. Anzala Sumro, can you please turn off your video? Anzala Sumro, can you please turn off your video? Because I get some distraction. Anzala Sumro, are you attending my class? Please turn off your video. Can you turn off your video, please? Because I don't know how to get rid of this stuff. It is okay. I can drag it. Okay. So this is the situation, and we are now going to use some sort of a power correction device. For example, for inductive loads, what I can use is I can use some sort of a capacitor, and what I do is I attach the capacitor in parallel to my load. Okay, why I do that? Why I attach the power correction device in parallel? For example, this is your 220 volt RMS in your home, 50 hertz, and all your appliances are attached to this 220 volts because they buy 220 volts 50 hertz supply. And if I had attached the capacitor in series to this load, let's say I am using the capacitor as a power correction device, and these are my inductive loads. And if I had attached the capacitor in series to my loads, then you know that as per the Kirchhoff's laws, voltage laws, the voltage sum in this loop will be equal to 220 volt RMS. That means part of this 220 will drop across the inductive load and part will drop across the capacitor. And then your load will not be getting 220 volt RMS. So a power factor correction device such as a capacitor is always attached in parallel to the load. And why we use a capacitor? Because I told you that the capacitor behaves oppositely to an inductor, because we know that the inductor, in an inductor, the current lags the voltage. Okay, I had told you a very convenient term, it is called civil. In a capacitor, I leads V, and in an inductor, I lags V. That means V leads I. What happens in a inductor? The current is lagging the voltage. So if the voltage vector is having a zero reference angle, then I is lagging. And in a capacitor, opposite happens. If V is this zero vector, zero angle vector, then I is leading it with a positive angle above the x-axis. Okay, so in order to offset this effect of lagging current, you add a effect of a device which has a leading power factor in which the current is leading, and together the two will try to cancel each other out to make the power factor unity. That means it wants to make the V and the I vector to align having a minimal angle or a zero angle. So in order to reverse the effect of inductor, you attach a capacitor, and it is always attached in parallel so that the voltage requirement of the load is also met. Okay. So now what happens is that since the capacitor is a device in which the current is leading the voltage, so what we now know is that we could modify this power triangle. Let me make some space over here. Okay, so now what happens is that for an inductor, we said that it's this is the same power triangle. We say that its reactive power is in this direction. Uh, this is your real power, this is your theta. So let's say if this is the power triangle for an inductor, then the power triangle for the capacitor looks like this. The real power is again in the same direction, but the reactive power is now in a reverse direction. Okay, otherwise the triangle looks the same, it just appears a bit inverted, because we know that in an inductor, the reactive power is stored being differently than in a capacitor, because they are like two opposite devices. So in an inductor, what happens is that you will say that if you have positive reactive power, then in a capacitor you are going to say that you have negative reactive power. The power of the real power has units watts, the apparent power has units volt amperes, and the reactive power has units volt ampere reactive. Okay, so similarly here, watts, volt ampere reactive, and sorry, this one should be volt ampere. Apparent power is volt ampere and real power is watts. Okay, so now the reactive power direction in an inductor and in a capacitor is opposite. So what happens if I merge these two loads? Then what happens is that the real power will still stay the same or maybe increased because of the requirement of this load and this load. So if you have an inductive load and a capacitive load, so let's say if the real power here was P1 and the real power here was P2, then the real power in the third case in which you merge the two devices will become P1 plus P2. But now what happens to the reactive power is that the reactive power will subtract from each other because of the difference in the direction. So the triangle, let's say if the effect of the capacitor is less than the inductor, then that means that Q1, case 1, Q1 is greater than Q2. The effect of the inductor is more than the effect of the capacitor. Then since Q1 is greater than Q2, then Q1 minus Q2 will be upwards. Okay. In the case 1, Q1 minus Q2 will be upwards. But now what happens is, since we are subtracting the two, the vector direction will also be upwards and its magnitude will also be small. Let's say Q1 is greater than Q2, so I do a Q1 minus Q2, resultant direction is upwards. Real power is added. And now my power triangle will look like this. So this is exactly what I wanted, that my power factor has improved. It is still a lagging power factor, but it has improved because this theta is now very small and A is approximately equal to P1 plus P2. Okay. And in the second case, let's say Q2 was greater than Q1, the effect of capacitor was more, then my power triangle would still look like this. And this time it would be Q2 minus Q1. This is the apparent power, this is the real power again. And now again we see that theta is very small like in this part, but in this part the overall current was still lagging because capacitor's effect was less than the inductor. In this one, the overall power factor becomes leading because the effect of the capacitor was more than of the inductor. But in both of these cases, the power factor has improved. As you can see that the apparent power is now much, much closer to the real power. Okay, so you can use a device such as a capacitor which runs at a leading power factor, and you could use it to bring the power factor, the bad power factor of your load back to close to unity. Instead of capacitor, you could also use a synchronous motor, because we have just seen that synchronous motor can also be run at a leading or a lagging power factor. So this is exactly what I'm asking you in this complex engineering problem. Let me flash it. Okay, so in this complex engineering problem that I've released today, it is due on 27th November, Friday. It is again from CLO3. So you have a 2000 volt, 300 horsepower, zero point 0.9 power factor, leading 50 hertz two pole Y connected synchronous motor. And it has a synchronous armature reactance of 5J ohms per phase and armature resistance of 0.3 ohms per phase. 50 hertz friction losses are 15 kilowatts and core losses are also 15 kilowatts. The field circuit has DC voltage supply of 200 volts and the maximum field current is 10 amperes. Open circuit characteristic is given below in the figure. So the open circuit characteristic is this, and it is important to note that you have already seen this graph before, and we had done this for the synchronous generator, and we know that the synchronous generator and the synchronous motor are the same devices. They are just the differences. In a synchronous generator, you give DC to the rotor and you give nothing to the stator. You extract the AC supply out of it, and you are driving the rotor through a mechanical energy. And in a synchronous motor, uh, you supply the stator also with a three-phase AC supply, and you also supply the rotor with a DC supply. And due to the electrical fields, the magnetic field interaction between the rotor and the stator, the rotor starts rotating. So you input electrical energy and out of it. Okay. Please turn off your mic. अगर कोई सवाल पूछना है, you can ask. Otherwise, please turn off your mic. Please turn off your mic. माइक किसने ऑन किया हुआ है यार? प्लीज माइक ऑफ करें. Please shut the mic. Please shut the mic. Please shut the mic. माइक किसने खोला हुआ है? प्लीज अपना माइक बंद कर दें. Please turn off the mic. प्लीज बच्चों ये बताएं जिसका माइक है उसको बंद करें. एक सेकंड, मैं वही सेटिंग चेक कर रहा हूँ. हाई कैन आई म्यूट एवरीवन. वही मैं सेटिंग चेक कर रहा हूँ. म्यूट मैं कैसे कर सकता हूँ?
तेरा माइक खुला हुआ है क्या? यासर कयूं किधर है? तेरे को मैं
ओके, थैंक यू. मैं इसकी सेटिंग सॉरी ढूंढ रहा था. आई कुड नॉट एबल वाज नॉट एबल टू फाइंड इट. मैं देख के रखूंगा. ओके, वी कैन कंटिन्यू. Okay, so from here we can see that this same graph could also be used for a synchronous motor, because the machine is basically the same. The machine is basically the same, and it is just the difference in how we operate that machine. So again, this y-axis is showing you the EA, and this open circuit terminal voltage is the EA of the device, because the primary induced voltage is still on the stator, not on the rotor, and this field current is being supplied to the rotor, which is DC supply. And these values are mentioned in the line voltage values. As I've told you, all the data in the question will be line. Okay, so now what this implies is that in a synchronous motor, the equation, what is the equation? The equation is you can get rid of this. The equation in a synchronous motor is supplied voltage, terminal voltage is equal to EA, and this is the phase value plus IA is the phase value into RA plus JXS. Okay, so this equation is always written in the phase value, and the open circuit characteristic would mean that for a synchronous generator, if you do not attach a load and you give it some excitation and you rotate the rotor, then this much EA would be produced. Okay, so the same value of EA can be plugged into the equation for the synchronous motor. when you give it a certain amount of excitation. Okay, so the EA values could come from the graph. Let me go back. Okay, so this graph will help you to find EA values at your corresponding operational point. Now it says that this motor has a particular aspects. How much field current would be required to make the synchronous motor run at a rated load and 0.9 leading factor? So the rated load is 300 horsepower. You are also given the losses. So you can easily equate the field current by looking at the graph and the value of EA. Okay, so V phi is given, EA you can read off from the graph, and you can find your operating point on the graph and find how much field current you require. Okay, in the part 2, if this fully mechanically loaded synchronous motor, so it is again run at the rated mechanical load at 0.9 leading power factor, and it is now used in parallel with some industrial load. And what is the industrial load? You are getting two induction motors which can always run with a lagging power factor, and it's telling you the values of their real power and their power factor values. So using this values, you can easily uh, calculate the real powers and the reactive powers, just as I told you. And you are going to use your synchronous motor to be running with a leading power factor in order to offset the effects of these two and make the overall power factor improved for the three devices than it was for the two motors alone. Okay. So now you attach this as a third load and it is running with the full mechanical rating. That means it is not unloaded, it is fully mechanically loaded with this much. Now, all the three devices are supplied by a voltage bus bar also operating at 2000 volts, which is the rated voltage for the synchronous motor, and this 2000 volts is the line voltage wave. Okay, so find the net power factor of the initial two induction motors, and when you attach the synchronous motor which is running at a leading power factor, so it should bring some improvement to the overall power factor. Okay, and in the third part, uh, what you want to do, this is the exact design question that I want you to do. And you, as a design engineer, you know that the synchronous motor power factor can be made lagging or leading by changing the excitation or the load characteristic of the machine. So you calculated a certain net power factor improvement in part number 2, but now you are loaded with all the information about the motor and how much power factor correction you can, best power factor correction you can get out of this situation, you have to do in part 3. Okay, so you can see how much is the best power factor correction that you can get by changing the operating point of the synchronous motor, like by reducing the load or increasing the load or making it over excited or under excited. So obviously you are looking at making it more and more leading power factor so that you can achieve the best power factor correction. So in this part number 3, which is the main part, you are going to look at the operating point, existing operating point of the synchronous motor in parts 1 and 2, and how much more you can squeeze out of it. Okay, so let's put it that way: how much more you can squeeze out of the synchronous motor in order to make the power factor more better and better. Okay, so this part 3 is the main part of this question. 1 and 2 is just what you have already studied in this course. So is there any questions? Okay, so it already tells you about the two loads, so you can calculate the net real power of the two nodes by using these relationships. As I just told you on the whiteboard before, you can find the net reactive power of these two devices. Since both of these devices are both are lagging power factors, so their real powers will be added up, and their reactive powers will also be added up, Q1 plus Q2. And when you want to find the combined effect of the three, then the real power will become P1 plus P2 plus 3, but the reactive power, net reactive power, will become Q1 plus Q2 minus Q3, because the two these industrial loads are running with a lagging power factor, but this third device is running with a leading power factor. Okay, so is everyone clear about this complex engineering problem? Okay, so part 1 and 2, it is just guiding you about the situation, and in part 3 is the main design part, in which you are saying, okay, I got an improvement of this much, but how much is the maximum improvement I could get? So you are going to design your situation yourself, and remember, in a design situation, what things you can do and what things you cannot do. Okay, so you can move yourself on this operating point. You can have any operating point on this curve. This is allowable. You could make the motor overexcited or underexcited, or you could make the motor with increased mechanical load or decreased mechanical load, or you could maybe remove all the mechanical load from it, because over here you are just using it as a power factor correction device. Okay, or you could do other stuff, but what things you cannot change? You cannot change this supply of the bus bar, because this bus bar is actually supplying the voltage to the industrial load as well as the synchronous. You cannot change this. Can you change the output mechanical power? Yes, you can. You can even extract no zero mechanical load. You could run the synchronous motor at no load. Can you change this? Of course, I'm asking you to change this. At 0.9 power factor leading, you will get a certain correction, but if you could increase it more, like 0.95 leading or 0.96 leading, then the improvement will obviously be better and better. Okay. Sorry, if you can make it 0.7 power factor leading, then the improvement will become more and more. Okay, so if this value becomes closer to 1, then you are running it at unity power factor. So in order to make it more leading, this value could be decreased to 0.8 or 0.7 leading. So then it would be having a better effect in cancelling out the effect of the inductive loads. Can you change this? You cannot change this. Can you change the poles? You cannot change the construction of the machine. Can you change the Y connected synchronous motor? No, you will make it. You cannot alter the construction of the synchronous motor. Can you change the windings? No, you cannot change the winding. Can you change the friction losses and core losses? No. This is depending on the construction of the machine. So some parameters are constant and some parameters you are going to uh, tweak. And when you are going to tweak them, then you are going to get some maybe better improvement. So this is the third part, which is the main design part of this question. Are there any questions? Are there any questions related to this? Okay, are there any questions? Okay, we are not going to do anything more after this lecture time ends. Then you can just go and do your other stuff. Okay, I'm not going to restart a new meeting because I'm not starting a new topic today. Okay, says everyone here. Abdullahi, have you understood the complex engineering problem? Is Abdullahi here? Abdullahi, are you here? Okay, because of you, I'm always switching to the English so that you can understand all the stuff. Okay, so I've already taught Abdullahi once before previously. He's a very nice, studious student, and so are you guys. Okay, so please complete all of these both assignments, assignment number 4 and assignment number 3 on time, and submit on the LMS. And inshallah, from next week we are going to study the topic of the DC machines. Okay. Okay, is everyone clear about the complex engineering problem? Any questions? No questions? Okay, so if you are having any doubts about this complex engineering problem, you can always ask me in the next class, and I will be very happy to oblige you. Okay, so uh, best luck to all of you. Good luck. Okay, and From the next class onwards, we are going to start the topic of DC machines, which is CLO4, the last topic. And uh, hopefully, do you know when the final exams are starting? Anybody knows what date the final exams are starting? Give me the correct date. Have you seen the academic calendar? And then you give me the exact date. This is because so I can pace myself. So if there is little time left, I will have to rush through the topic of DC machines, 6 December. So that means we still have about 17 plus 6, almost 3 weeks. So DC machines, I think, will be over in 2 weeks. And that will leave us with 1 week for the revision too. Okay, so uh, this topic of synchronous machines, I think we have covered all the main major details. And by no means I'm saying that you have become an expert of this topic as well as the other topics we have covered in this course, because in a semester system, the time is very, very compressed. And we are also studying in online manner. So it is somewhat a suboptimal method. So you always have the textbook with you. Try to read the extra topics that you can in your spare time, because that will broaden your horizon for you. And whenever you go for an interview, then you will be knowing all of this stuff. For example, I'm going to tell you one or